be. So I'm not necessarily expert in any of the math topics I present. I'm a software developer here at Improving, full stack developer. I'm minored in math for what that's worth. So I know more math than the layperson, but nothing that makes me like an expert or anything. So a lot of these ideas sometimes are new to me, and I'll explore them and present them. So sometimes I'm learning with you. And again, everything here is in Python. It's all written to be very obvious, right? So I'm worried about how efficient is this, or is this properly refactored? It's more like how obvious is this for what it does? Because the purpose is to use this to illustrate the concepts. And anything I give isn't business advice, so use at your own risk. And any opinions I express aren't necessarily those of my employer. Now, don't be afraid to ask any questions. Stop me at any time and ask questions. Definitely, this is very informal. Okay. So, what I want to talk about today is abstract algebra and how it is something that can help us write a different kind of automated test. Specifically, a type of automated test called property-based tests or generative tests. So if you're a software developer or a QA, you may find this particularly relevant. I imagine everyone here kind of falls in one of those categories. And yeah, there's definitely a connection with abstract algebra, all those really kind of, when am I ever going to use these things you read from school? We're going to talk a bit about that. And specifically, we're going to focus on the idea of an invariant. These properties, these relationships among operations, among things, and how we can use that to write very general tests. That can give us a lot of test coverage. We'll also talk a little bit about how we establish evidence or confidence that some properties do hold. And we'll talk a little bit about proof versus argument versus statistics and where that factors into this. And all of this blends into how to write these different kinds of automated tests. So we'll start with abstract algebra. And I kind of put this in parentheses, and maybe I should put it in quotes. So you're probably familiar, and maybe you're trying to forget, the algebra you learned in school where you had to solve equations, right? Two trains are coming at each other in the night, et cetera, et cetera. That's not that. This kind of abstract algebra doesn't concern itself with equations. It doesn't even concern itself with numbers. It really just concerns itself with the idea of operations among objects that may or may not be partly specified, and then starts looking at these relationships and what sorts of universal laws can you draw out. And abstract algebra is a very big field. It gets into a lot of like really just complex stuff. People spend lifetimes studying this. So we're just touching the surface, just staying on the surface level of this idea of relationships and how we can take advantage of it. Okay? So we want to start off just talking about the idea of quantifiers. Okay? So whenever you want to talk about something, you want to express something universal, or even, something universal, sorry, that, you want to use what's called a universal quantifier. And it looks like the upside down A over here. And it's pronounced for all. So if I say for all x, this is a set membership operator, for all x in subset M, some property P holds of x, right? And all we're saying is that every single thing in x is true. That's what for all x means. So for example, if I say for all person, such that a person is in a set of bachelors, this person is unmarried. That's a universal statement that holds that exception for everybody in that, okay? And I'll call this an invariant or universal property when you phrase it this way. But then you also have what they call the existential quantifier, and that looks like a backwards E, and that's pronounced there exists. So there exists an X in a set of M such that P of X holds. And that just means there is at least one element of the set in M for which this thing is true. So for example, there exists a bachelor or a person in a set of bachelors that is unhappy. So you're saying basically there's at least one bachelor in a universe who's unhappy. I've met all bachelors, so I don't know, but I imagine there's probably at least one of them, right?
All of them are unmarried.
Oh, wow, you say all of them, so you're saying it's supposed to be universally common, right?
All of them are unmarried.
Oh, well, yeah, and all of them are unmarried, yeah, all bachelors are unmarried, and that's a tautology, right? And then that's actually a good point. When I use the example of bachelors, like for all persons such that X is in a set of bachelors, X is unmarried, right? We know that's true because by definition, a bachelor is unmarried. And this is called a tautology, okay? And really in math, all proofs are tautologies. They just sometimes can take you hundreds of pages to draw out the tautology, right? So just because something is true by definition doesn't mean it's obvious. Sometimes, it can take you forever to discover it, or you may never know. But that's essentially what it is, really just studying tautologies. And that's really what the only thing we can say about universal quantifiers, is that it has to be a tautology for us to really be able to make this statement with any kind of confidence. So far, so good? So properties. So any kinds of things you could say about objects or operations are properties. P of x, for example, is a property, right? X is greater than y. That's a property. It's a statement about things, or it could be about relationships. It could be about even values. And in the case of like universal properties, they don't change. They always hold, and they hold for everything. And it's these invariants and specifically universal quantifiers that we are interested in focusing on, no matter what these cells. So let's talk about some properties that we learned about in school, and even some we didn't. And these actually are going to come in handy. So we learned about commutativity, right? That some operations are such that the order doesn't matter, right? For example, if I say f of x is equal to, look at this. So if I say, for example, f of x is equal to f of y of x, okay? For example, x plus y equals y plus x. That some operations, the order doesn't matter. For all x and y in some set that the operation is defined on, x plus y is equal to y plus x. That's called commutativity. We're used to seeing it in math, but there are other cases outside of math where we can also see it. Okay? Transitivity. An example of transitivity. If x is greater than y, and y is greater than x, that little caret, that little upside down v, that's and in a more formal Boolean notation. If x is greater than y and y is greater than z, then x is greater than z. And the idea is that you have a relation holds between two elements, and another holds between the second element and the third, then that relation holds between the first and the third. Okay? And it's almost like, you can even think about it even in terms of family. If x is related to y, and y is related to z. Well, I don't know, is x always related to z? If one person is related to another person, like say Bob is related to Sally, and Sally's related to Jane, is Bob related to Jane? I don't know.
No.
Not always, why not? Why not?
Oh, man.
Yeah, you're on the spot. You're going to be the leader of this group, so you better answer.
I don't think it follows.
Yeah, why not? You can just give me a counter example. If you give me a counter example, I'll set up to disprove it.
There could be a case that they're related by, well, I guess they're still, if they're related by marriage, then I guess you're still related. What do you mean by related? This is going to get ugly.
Okay, okay, good. So let's make it easy. Let's say it's a blood relation.
Okay, then yeah, if I forget what variables you use, but if A and B are married, and B and C are related by blood, then A and C aren't necessarily related by blood.
Okay, cool.
But the family you married into, you're not blood related.
Okay.
That's the point.
Yeah, that's true. Okay, what about this? What about the relationship is a friend of? If Bob is a friend of Jane, and Jane is a friend of Sally, is Bob a friend of Sally? No? Good? Yeah. No. Social networks want us to think otherwise, but no, right? We have a lot of friends that we can't stand, right? I mean, right, exactly. So being a friend of is not a transitive relationship. So these kinds of relationships apply to, they don't have to apply to numbers, they can apply to people, they can apply to structures, strings, ideas, right? Very good. Then there's also the idea of a zero element, where there's some special element and some operation where if you use that element on every member of a set, you always get that same constant value. For example, multiplication. The zero element for multiplication is 0, duh, right? Because anything times 0 is 0, right? No matter what number you have, if you use the 0, multiply it, you're going to get that same a constant value, which is 0. Okay? Then there's the identity element, right? That there is going to be some elements, again, some constant where whenever you apply an operation and some operation with that constant, you always get the same value back. For example, in multiplication, what is that identity element? 1, right? For addition, that identity element is 0, right? If you're looking at it in programming terms, for example, we can use this example. If you have a string, assuming a set of strings, and you have the string concatenation operator, the identity element for that is the empty string. Because the empty string appended to any string is that original string. So it applies to something even beyond numbers. Then you have this fancy word, idempotence. And all this means is if you take a function and you apply it once, it's the same as if you applied it any number of times. Okay? And you'll hear system administrators and DevOps talk about idempotence a lot. They'll say, oh, this operation or this utility is idempotent. And all they mean is if you run it on a system and it configures your system and you run it again, it's not going to change the system after that. And it's very useful to know because someone might be like, oh, I want to run this in a script. How do I know if it ran before? Maybe it'll screw things up. They say it's idempotent, it's like, don't worry about it. Run the script again, you're not going to break anything because it's idempotent. So you'll hear system administrators talk about this sometimes.
Why would you want to run it again if it's not going to change anything? Why would you want to
because it might be that you don't know if it was run, and it might be like a startup script, and you didn't know if it was run, you're like, okay, I need to do whatever, somebody comes in, let me run this to make sure everything's set up. Maybe it was run, you have no idea, and so you run it. Or it could be that, and this is a really good question, or it could be that this particular utility is part of a bigger setup process, and the setup process does different things, but this utility, if it, maybe, again, it's idempotent. So maybe you need to run that other setup process to configure some things, but it's going to rerun that utility as part of, you want to make sure it's not going to break. That's a really good question. Yeah. Because otherwise, we never did anything wrong. Yeah. Yeah, and so an example is a program of idempotence. Sorting. If you take like a list or an array or a collection, and you sort it, what happens if you sort it again? Yeah. Same thing, right? Same thing as if you sorted it once. If you sorted it 1,000 times, it's going to be the same thing as if you sorted it once. So sorting is idempotent. Then you have this idea of an inverse, right? So for example, if I take a function, and this circle it just means composition, right? Like f composed of g of x is the same as saying f of g of x. So inverse just means I have some function that reverses my function and brings me back to my original. So for example, let's say you have a function to reverse a string. You take a string, you pass it a string, and it returns a string in reverse. What is the inverse of that function?
Would it be -1?
Was what? I'm sorry.
-1?
Oh no, I meant so by inverse. I meant what undoes that function. Yeah. So like, let's say you have reverse. Hey. So yeah, let's say you have a string called reverse. You have a function called reverse, and it takes a string and it reverses it. And you want to know what function that if I apply to reverse gives me back the original string. Okay, I'll give you a hint. Let's say your string is ABC. Now if you apply reverse to it, what do you get? CBA. You get CBA, right? What would you need to apply to CBA to get ABC again?
Oh, right, yeah. It's own reverse.
Yeah.
It's its own inverse.
Reverse is its own inverse. It's a bit of a trick question. If you apply reverse to a string, you get the reverse string. If you apply it again, you get it back, right? Another example is encryption and decryption, right? Encryption and decryption, they're inverses of each other, right? Does that make sense? And then you have this idea of an oracle, and this goes by a few different names. But the idea is that you have some function that is equivalent to another function, right? That you could use another function to test this function. Now, and in programming, this comes in handy because sometimes you want to write an optimized version of a function, right? Maybe there's already an implementation that's built into the system, but you have a way you could fine-tune it, and you need to make sure it works. Well, if you already have a slower version that you know works, you use that as your benchmark to test against. And so you can use that as your oracle. Okay? Questions? Cool. Hey, remember, if you need access to the sheet, give you a sheet, you'll get access to everything. So, okay. So an idea is that all of these properties and more are ones we can use to help us in testing. And I'll show you how and why we want to do it this way. So now when you have properties and you want to start establishing whether or not they actually hold, you have a few different ways of doing it, right? And I'm going to call them generally arguments. Proof is like a gold standard. It is the gold standard, right? Because proof tells you, no, this is true, it's true for everything, done, we're happy, go home, right? That's proof. And with proof, you have a few different ways of doing it. If you're dealing with like Booleans, you can use truth tables. The nice thing about Boolean values is that you only have true or false, or 0 or 1. And so if you have a function and you only have a handful of Boolean variables, you can actually show every possible combination of inputs to the function and basically so I proved that this is, for example, never false because I just showed you every possible value, right? Good luck at doing it with integers or reals or anything else. So exhaustive enumeration actually is viable for Boolean truth tables if your inputs aren't too much. And then you have the more analytical arguments, which is what we all know and love or hate from math, right? And these are the ones where you start from definitions or axioms and you start drawing implications, right? You know, for example, you know, a triangle can only have, you know, no more than one 90-degree angle, and you're like, well, because the triangles, you know, angles have to add up to 180. You kind of draw on and show how you absolutely have to, this has to hold because of the definitions. And sometimes we'll even do the reverse a little bit and do a proof by contradiction. By, hey, if we assume this is not true, it leads to a contradiction, therefore it must be true. And I think like the rationality of the square root of 2, I think was one of them, and infinity to the primes was another that they use like proof by contradiction. But they're all generally analytical. You're just taking like, you know, the definitions, your axioms, or even other things that were previously proved, right? You can use that, theorems, and then you start to show the implications, right? And then, but of course, we don't always have the luxury or the patience to do all that. So a lot of times we just go for evidence, right? Evidence is weaker than proof, right? Evidence is like, hey, you know, let's go ahead and make a reasonable argument. Let's go ahead and say, throw some values at it and see that, hey, we throw a bunch of values, it looks good, I'm happy. And we kind of call that a day a lot of times. And that's usually what we do with testing. And it is weaker than proof. It's not going to be anywhere near as exhaustive. And you know, you can have evidence and then find out later that, oh, this thing wasn't really true, right? Yeah, you tested 10,000 values, maybe that 10,000 first value was the one that broke it. And you can make your evidence-based approach a little bit more rigorous if you are a little bit more systematic about how you pick your values, right? So for example, you know, if you're, you know, you can say, hey, well, let's go ahead and take a more statistical approach. Let's get values for a particular distribution. Let's make sure I have a whole bunch of values where I expect this phenomenon to really like, you know, cluster. Or let's make sure my sample is unbiased, right? You have ways to try to pick your data so that at least you're less likely to, you know, to be thrown off by not having enough evidence or even having really badly clustered evidence, right? You know, I can pick 100 values, well, I'm not going to be in a range of say 1 to 500. I want to test a few, let's say thousands or millions. So far, so good? Okay. So that brings us to automated testing. Now, how many of you are familiar with automated testing or have done it or have heard of it? You know, okay, we got one. So I'll give you an intro to automated testing. So when you write software, you can actually have your software, you can write software to test code. And it's not as difficult or weird as it sounds. And these are called automated tests. And there's a bunch of different kinds of automated tests. You've got unit tests, you've got integration tests, you have end-to-end tests. The QAs are generally focus a lot on. Programmers are generally going to focus on unit tests and integration, what the use of integration. And you usually have a framework that you run your tests through. And it's generally, and automated tests are great because they run your tests very fast, right? You're gonna have hundreds or thousands of tests running. You know, it's software, so it doesn't get tired, it doesn't make mistakes, it doesn't skip out on tests. And because it runs fast, when you write your code, you write a little bit of code, run your test against it, make sure you didn't break anything in your code or in other features, add a little bit more code and run it. And there's even entire processes designed around programming with automated tests. Test-driven development, TDD, and even behavior-driven development, BDD, are two big ones. So it's a pretty useful practice. Not everyone does it, but quite a few people do, and it's quite useful when you use it. And the structure of your test is pretty straightforward. So here's an example of a test. Usually we're going to use a framework that'll do a whole lot of stuff for us. So you can even like throw it in as an assertion. This is very ad hoc, but it still does the trick. So here, for example, I want to test this function called divmod. Divmod is a built-in Python function. It takes two values, okay, divisor and a dividend, and it divides, right? In this case, it divides x by y, and then returns a tuple consistent of the quotient and a remainder. So basically, it does division and gets the remainder. Okay, that's what divmod does. Okay, so I say, hey, I get this function called divmod. Let's pretend I wrote it or I never saw it before, and I want to know, does it actually work? Okay, well, I'm going to pick two values whose results I know, right? 10 and 3. Numerator 10, denominator 3. I know what the result of dividing and getting the remainder are. So I'm going to pass those in, and I know if this thing works the way it's supposed to work, it's going to give me back a 3, 1. A quotient of 3, remainder 1, right? 10 divided by 3, 3 with a remainder of 1. Okay. And so what I could do then is I could say, okay, cool, well let me call divmod, and then let me run an assertion to actually confirm that the result that came back from divmod is the result that I expect. That divmod of this is this guy right here. And assert just checks a condition, and if it's not true, it'll report it or bring your program to a screeching halt. Okay? Now if you're running this in a test framework, you'll have something called assert or usually expect. And it'll just report, hey, this test failed with these values, this test passed, this failed, right? And this way you know, hey, did this work? And so I can run this, and I can see here when I run it, hey, cool, nothing happened, all's good. Silence is a good thing, right? But let's say that, let's say that maybe this thing actually, I put it like I got something wrong. Then it gives me a big fat error and tells you, hey, yo, you suck. This is what happened, right? You expected this, but you got this. And so this way you can see that I have a whole bunch of these tests, right? That I can get more confidence in my code. So I have like a bunch of functions, and for something like divmod, I may have 10, 20, 30, 100 values, and I just scatter them, and then I test another function. These are all the functions in my code base, and I run these tests. And then anytime I make a change, maybe I decide I want to re-implement divmod, make it more efficient. I go and make some changes, I run the test again, oh crap, I broke it. So this thing can be very useful for development, right? Does that make sense? Okay. And again, depending on what framework you have, every language I know of has pretty solid automated testing frameworks. So if you're in JavaScript, you've got Jest, C# already has a bunch of stuff built in. It has a test runner built into Visual Studio. So you got a bunch out there. And if you're interested, let me know, and I can tell you some good ones on the platforms. Now, this particular type of test is an example-based test. Okay? This is a type of test that most people write. And most people just know this as test, because example-based tests are like the default. There's so much the default that a lot of people don't know that there is another type of testing you can use. And you can use it in addition to example-based testing. It's not a competition. And it's called example-based testing because you pick examples and you test them, right? I picked the example of 10-3, and I tested it against the expected result 3-1. And then I picked more examples and more examples. So the other type of testing is a property-based test. So whereas in an example-based test, you pick the values you want to test, okay, and you run them. In a property-based test, you don't pick your values. You use a framework that's basically going to choose the values for you, and you have no idea what it's going to pick. So let that sink in for a moment. You're going to write an automated test to confirm that, say, div mod works, but you have no idea what x and y are, and your test has to pass. How do you do that? So, sure. So let's say I'm writing a test now to see if div mod xy returns the expected results, okay? Or at least it's correct. Let's say it's correct. But I don't know what x and y are. So someone says, hey, test div mod. I'm not telling you what x and y are. I'm going to generate, say, 100 random values for x and y. You're not going to know what they are, but you need to write an automated test. And it doesn't necessarily even have to check that this is correct. It has to check that some aspects of it are correct without knowing the values.
You can use the random number generator.
So the random number generator will give you these values, right? And in fact, if you use a property-based testing framework, it'll generate these values for you. So the random number generators, yes, that'll give you the random values. Now that you have the random values, how do you know that div mod works?
One property you get first, the remainder is always less than y.
There you go, and you got it, right? You said the magic word, property. So yes, we pick random values, that's absolutely correct, Pac. And we check for properties. Remember all those properties I showed you? Things that universally hold? If we find properties, things that universally hold, it doesn't matter what x and y are. I know what has to hold for a division or div mod. And yeah, Kai had a good idea. He said, hey, you know what? No matter what x and y are, your remainder always has to be less than your divisor, right? Right? So whatever x and y are, I know that the remainder, this second guy, has to be less than x. So that's one test I can have, right? And that's one property. Now, and I can test more properties. I don't just have to test one. I can say, okay, I know that. Okay, let's see. What about another property? How about an invariant? Is there an invariant I could use here? Huh?
The remainder divided by the quotient. So something you do will always give you back the x value.
The inverse function, right? You said it. Division does have an inverse function. If I have a division, right? If I get a quotient and a remainder from some division, right? I know that the original value here, right, is equal to, oops, this is the quotient, yeah. Quotient times y, x is equal to qy plus r, right? 10 is my original value, 10 is my quotient, 10 is my divisor, 3 is my dividend, right? So 10 divided by 3, okay? Well, I know that if I say, hey, 3, 1, well, let's see, 3 times, this was 3, 9, plus remainder 1 is 10, right? Because division has an inverse, and this is our inverse function, right? So yes, I can put that in, and that's a very powerful one. If you can find the inverse function, you have a test for total correctness. You can use that test and you're like, okay, done. If you can't find the inverse, you probably want to add enough properties that you feel confident you narrow in on the behavior, right, of division. Excellent, yeah. Now, if you didn't have this, you can keep thinking of other things. Hey, is there an identity element? Hey, okay, right? Well, what if y is 1? I'm always going to get back x 0, right? No matter what. Because anything divided by 1 is the thing, and the remainder is always 0. Hey, is there something that's going to give me a constant? Yeah, if I divide x by itself, I'm always going to get 1, 0, right? No matter what x is. So all these different properties, you can start putting up through here, and you're like, oh, okay, cool. Does that make sense? Now, and the reason why you want to do this is when you do a property-based test, it's going to give you two nice things. First, it's going to generate a lot of values for you. And again, like I said, it's fairly easy to generate them ourselves, right? Generate random numbers. But a property-based testing framework can generate random numbers, random structures, random strings. Some of them are smart and generate things that look like email addresses, and then it'll run a bunch of tests for you. So you could run like 100 tests for you. and it'll generate them randomly enough that it can help get past our test bias. Because a lot of times we test and we don't stop and think about these really weird cases. Well, our property-based testing framework will. So whereas here I have to say, okay, I tested 10.3, what else do I need to test? And out of the values, it's gonna say, nah, here's 100 random ones. And maybe I'll throw some stuff actually you never even thought about, and let's see what happens, right? Maybe an email string, strings that you're testing, maybe you never thought about testing an empty string, or the one that ended with an at, right? So they get you past test bias, and they also generate a lot of values for you, so you get a lot of test coverage. Now, if you only tested properties that aren't equivalent to the actual function behavior, you're testing a small slice of behavior and you get a lot of test breadth, but little depth. But if you add more properties, you get more and more depth, and you start to approximate the behavior of your function with a lot of tests. So Python, and every language I know of has a property-based tested framework. Python has one called hypothesis. It's unfortunate that it's called that, because if you try to Google hypothesis test, it'll take you some stuff on statistics. So it really sucks trying to find documentation. But hypothesis is something for Python. For C# and F#, there's FS check. For Haskell, there's quick check. I think JavaScript has JS verify. I think there's Scala check for Scala. Just about every language is gonna have some property-based testing framework. I mean, some are better than others, but they all exist. So hypothesis is the one, and you know what, we need this to do feature list. I love this to do in here. So hypothesis is one that is available for Python. And again, you can install it just by pip install hypothesis, okay? And that's really it. So we've installed hypothesis already here, and now I want to say, hey, I want to run this test on divmod. So here's how we use hypothesis. So first I'll say from hypothesis imports, and then I'll import all things I want. In this case, and I'll explain each one of these as I get to them. But I import everything I need from hypothesis. Or if I just want everything, I can just import star. Next, I have my function that tests, okay? Now above this function, you see this @ sign, this is a decorator. And what I'm saying is, hey, for x, generate some integers, and for y, generate integers. So this will pretty much say, okay, I'm gonna run this function below me with random integers for x and y, and I have different kinds of generators, and I'm gonna run it for 100 times. So I'm saying, okay, well, cool. Now I'm gonna go ahead and write my test. And the test is, like I said, okay, well, the quotient and a remainder, okay, from divmod, okay, well, I know that, okay, I'm gonna go ahead and say, this is my result of my inverse function, x1, multiply y times the quotient, add the remainder, and I expect that this inverse function result, x1, is equal to the original divisor, right, x. And if not, spit out this error message, okay? Does that make sense? And I was going to run this 100 times. So I don't know what x and y are. All I know is I'm going to get random numbers, random integers, and this test I expect to work for everything. Remember, for these tests, I want universal quantification, right? I don't want existential, because if I say, yeah, it may hold, well, there's going to be a bunch that doesn't hold for it, it'll fail. So when I run this, what do you think will happen?
Does it include floating points?
No, it's just integers. I said it's not integers.
Where's the random?
Oh, it's automatic. When you say given right here, when you say given, it says, hey, generate for each of these positions random integers, and then it feeds them into x and y. Yeah, that's how the property decorators work. So I'm gonna run this, and this should work perfectly, right? Not a single problem, right?
What's the red?
Huh?
What's the red?
Don't worry about this red. Don't worry about that. This should work without a problem, right? Perfect.
What? Yes.
Hey, I run it, right? I'm like, come on, just run it.
Yeah, I don't see any problem.
Okay, so we're gonna run this. Notice how it's taking some time, and division by 0.
Yeah, you didn't exclude the 0.
Yeah.
That's impossible.
Right, yeah, it covers 0. And so this shows one of the useful things about it is, like, if I was testing this manually, maybe I just mentally would never have bothered to test with 0, because I'm like, well, division by 0 is illegal. That's great, but if I'm writing a function and there's an error condition, I have to know how my function behaves over that error condition. So not even testing 0 was a bias I had. And by taking the test data out of my hands and randomly generating it, it tested on areas that I didn't even think about. Yeah, okay, 0, duh, I gotta cover 0, right? Okay, cool. Now, so again, if we were writing this function, we could decide what we want to do with 0. Do we really want to throw an exception? Do we want to actually return, like say some kind of special, like a NaN type of number? I actually worked at a place, it was a market research place, where division by 0 was actually a special division by 0 that we wanted to allow, because there were cases in market research where you're trying to divide by a population, and a population could whittle down to 0, and if that's the case, you just get a 0 back. So we actually wanted a special division function that divided by 0. So this would have caught like, hey, your calculations are covering this case. Again, mathematicians will hate me for even writing something like that, but that's something we needed. Okay, now we could also just customize our data generation. Okay, so the nice thing about hypothesis, and really any property-based testing framework, is you can customize your data generation. Okay, and I'm just scratching the surface, but I'm trying to give you an idea of like what this is about. So there's a ton of things you can do that I haven't even researched or even shown here. So in this case, again, I'm calling the same thing, but this time I'm saying, hey, st integers, right? For the first integer, that's going to be x. For the second one, make sure my minimum value is 1. Now, st here is, I believe, positive is non-negative integers, okay? So the minimum value, actually no, it's any integer, sorry. So minimum value is 1, pretty much ensures that this guy right here is going to be a positive integer, which means I'm not going to get a 0. And we can actually feed in arbitrary predicates and so on, so we can make it even more refined, but I want this example to be simpler. Okay, so let me test this one to see what happens. And boom, it passed, right? No results, and no news is good news when it comes to testing. Okay? Although again, if you're running this from a command line, it would actually report every test until you passed. Since I'm running this from inside a notebook, it's just like, hey, yeah, I didn't say anything, so that's good. So far, so good. So, okay, so what if I wanted to test a function that wasn't math, right? I just showed you some math examples. Let's get into some non-math examples. So, hypothesis had an example with encoding a string, right? Remember how I talked about encode and decode, right? So, okay, let's do this. So over here, we've got this function to encode and decode, right? And remember, we're like, hey, what can we test if I get a string that comes back, and I don't know what the string is, and I want to test that I was encoded or decoded properly, what can I do? Exactly. And this is where the idea of an algebra comes in, because now I'm testing, but I'm not just testing encode. I'm like, you know what? Let me test the relationship between encode and decode, because the two functions live together, they obviously relate together in a certain way. Let's go ahead and test them together and see that their relationship holds. So sometimes you're not even testing a function alone, you're testing 2 or 3 of your functions together because they all should build up together. And again, some people who are a little bit more into formal methods will say that, your function signatures or your method signatures form an algebra, and start talking about these terms. So like, okay, yeah, so let's test that they're inverses of each other. Now, I have this really cheesy implementation where I just return the string, right? So I just declare encode and decode to both be the identity function, right? And so I'm like, okay, so I'm gonna go ahead and say, hey, generate some random text, okay? I'm gonna say this, okay, now I'm like, let's go ahead and decode the encode, and I'm expecting that the result of this is equal to the expected value, which is really the original value. Now, and if I run this, okay, I'll give it some time. So I run this and it works, but it's kind of crappy because this is just the identity function, right? Right? I'm like, okay, sure, it worked, but then I just returned that. So I'm like, you know what? Okay, fine. This shows you that even though you write a lot of tests, there could be, of course, some gross failures that can slip through. So how do I guard against that? Well, I start throwing more properties at it. I'm like, okay, you know what? I already tested inverse, fine, but I need something where this lame implementation doesn't work. So let's see. I'm like, well, what's another one? Oh, how about this? What's one property of encode? Well, if I encode a string, the result that comes back should be different from the string I passed in, right? Okay, seems reasonable. Again, it's a broad statement, but it is one that, I figured we'll catch the error. So I'm like, okay, cool. So let's just go ahead and make sure that that the encode of x is not the same as x. The result has to be different. And so I run this, and of course, it's gonna fail because, right? I just have the identity function. And so now I want to think about these two tests together. One, we're testing an inverse, which, okay, pretty broad test, but I'm also testing that the function is not an identity function. Remember, we're looking at these two tests collectively. Running like, say, 100 samples on both of these can start to flush out some errors. And I'm like, okay, cool. Very well, looks good. Okay, well, I figure, let me go ahead and start kind of trying to game the system, right? Let's intentionally get cheesy. I'm like, okay, well, here's what I'm gonna do. My encode is just gonna be the string, and I'm gonna append an empty string after it, and decode is just gonna remove that thing I added in here, right? Right, and so I'm like, yeah, and okay, of course it passed, right? Because one, this is the inverse of this, and adding this does change the original string. Okay, so I'm like, maybe I need another test to help guard against the cheese, right? So I'm gonna be like, okay, well, let me think. If I want to have a test for encode, and I want this test to ensure that I'm not just doing appending a string always gives you a total checkout value that is going to be greater than what you had before. Take it away, less than you had before, right? Taking all the items out of your cart, that better be zero no matter what those items are, right? So you can have random tests that hit even a website, and you can go ahead and check these properties and make sure that your website behaves as expected. So it doesn't even have to be code either. And I've actually written, like 2 or 3 times I've written actually 4 websites. Questions so far? Cool. And we're getting close to wrapping up. So I'm gonna just close with there's really we're close to wrapping. So I also ran into that same market research firm where we used that div 0. I'd also written the property-based tests for it. That's the first time I actually used property-based tests. And like Tak was saying, I actually randomly generated my own data because I didn't have a framework, right? So what happened was it was market research, so we had like a bunch of survey information online, right? And the survey information would have, and if this sounds familiar, a lot of my case studies come from my days in market research. There's a lot of fun stuff there. So a lot of the surveys would have data for people in a particular market, like say Houston. Who ate McDonald's in the past week? Who's planning to go to a movie theater? Who owns Nikes? What income, who has an income between say $50,000 and $75,000 and so on. And so we'd have this massive survey, and it would be pretty much, and they would interview a bunch of people, like say 750 or 1,500, depending on the market, and we have all this information there. And so the idea was, okay, cool, we have all the survey information, we've got an application. I want to test how, I want to make sure that our online application works properly, right? Now, I've already done some unit tests and so on, but I wanted to also start checking with like some random data and live data. So the first thing was like, okay, what invariants can I use? Now, we had a survey, and what we did with the survey is we broke down everybody by demographics. So for example, we had, genders, right? So you had your total adults, right? That was everybody. Then we break everybody down, break them down by gender. Then we take these total adults, we break them down by income level, age level, marital status, numbers of children, and so on. Well, every demographic group would sum to total adults. So if you took all of your genders and you sum all of their values, they'd always be equal to the values for total adults. If you took all of your income levels and you summed them, they always sum to total adults. Because we always had like not reported or zero income or whatever, right? So we always covered everything. So at this point I was like, oh, hey, okay, well, guess what? That's my invariant. So I actually ended up writing a property-based test that I feed it a survey, any survey I wanted. It would randomly generate some targets like, hey, let's find out who's planning to go to the Caribbean in the next 6 months. And then it would say, good, whatever this value is, make sure that when you sum all of the age groups that are going to the Caribbean, they're equal to all of the adults that are going to the Caribbean. All of the marital statuses going to the Caribbean equal to adults, and so on. And that was pretty much like the property-based test that I used, and I ran it. And it was great because it actually caught errors, but not in the software, it caught errors in the data, because there was corrupted data that we were catching. And it worked out so well that we ended up actually using it as our data validation tool. So the QA people who produced the data just basically recycled this thing and became part of their validation tool, and they caught a lot of errors before it got to clients. And this was done basically by just finding some stock invariance and testing it. Because again, if your data is corrupted, the odds that it's going to slip through any kind of halfway decent check is pretty low, because usually they get randomly distributed. Does that make sense? Okay. And then just some things to keep in mind, right? Whenever you use a property-based test, keep in mind that you're using sampling, right? You're not establishing property through proof. It's not like going symbolically and proving that this function does have this property. What it's doing is it's saying, hey, I'm going to pick a random set of values, usually 100, but they'll let you customize. Every property-based testing framework I know of lets you customize. It'll pick like a random sample, usually of 100. I'll throw them at it, and then if it holds, it says, hey, this property holds. Which is great, but remember, it's not a proof. It's always possible that maybe only 1% of your data causes the bug, right? Something to keep in mind. You also want to think about what kind of distribution is being used. Again, you can customize this, but again, if you're like, for example, and I've used this example before, if you've got like an application that's maybe related to like, fitness, and one of the things it takes in is like a person's heights, then, randomly generated, heights from say 0 inches to like, 10 feet, fine, but you really want to focus more on like say a normal distribution. So you want to start thinking about the distribution. Is it relevant, right? And so because if not, they could, lead you astray. You want to make sure again that this thing's picking a wide range of values. Some property-based tested frameworks, for some reason, will pick a small, narrow range of values. So you say, hey, I got a set of integers. It's like, okay, I'll pick 100 random values. And this 100 random values live in a range of 0 to 1,000. Like, dude, I'm using integers. I've got like, what, 32,000? If not more, if I'm using like more than 16 bits, right? Which a lot of times you are. So yeah, and a lot of times you can specify this range, but that's something to keep in mind, right? And again, sometimes you may have errors that live in a cluster. For whatever reason, certain values may trigger certain paths in your code, and your errors may live there. So you have one branch that's fine, another branch is where your errors are, but the branch is so rarely exercised that sometimes you could pass over it too. That makes sense? Cool. And then yeah, so basically being able to customize the sampling is important. So every so often when you run your tests, just check your sampling, adjust your sampling to kind of make sure you're hitting the broad range that you want. That's really about it. We've got a link to hypothesis documentation, which tells you a lot more. I barely scratched the surface of hypothesis. And again, whatever language you're using, you most likely have a property-based testing framework for that's going to give you quite a bit out of the box. Questions?
Your encode and decode testing examples that look like, is that what test-driven development looks like?
Ah, very nice, very nice. So test-driven development looks similar to this. So normally test-driven development, they'll use example-based tests. For test-driven development, they normally use example-based tests, not property-based tests. You could do it a property-based test, but it's not common. And the reason is a lot of times when you do a test-driven development, you usually are still trying to discover a function, but you know at least what examples should work. Whereas the properties, you have a better, deeper understanding of your function. So, but it is similar. So one, you normally use example-based tests. You'll usually write the test before you write any code, and then you write the code really cheesy just to pass the test, and then you start, beefing up your test and you start adjusting your code. Yes. And again, and a lot of times you're not going to necessarily write your code to try to fake out your test, but you start with like very simple implementations, get your test to pass, and then adjust it until you get something like the simplest thing that could possibly work type of thing. Yeah, so it is a similar workflow, but without so much the conscious attempt to game your tests. That's a really good question, yeah. Other questions? Okay, cool. Awesome. Well, so before we wrap up, just a reminder. So this group, I've got a new role at a client, so I'm having to get up early in the morning. So I'm passing on leadership of this group to Nick. It's probably gonna be, I guess, it's really gonna be his vision from here on in. So it may be a more informal group, whatever, but that's totally up to him. I'm just kind of letting you know. What happens is up to this guy right here, but.
So if you don't like it, blame him for putting me in charge.
Yeah, blame me. I won't be around, so blame me all you want, because I'll probably be in bed, passed out. But yeah, but Mike, yeah. So but again, whatever works for y'all. What you want to do a user group, whatever. I mean, it's totally up to you. And again, I'll try to be in touch here and there. If I can make it one day, I definitely like to pop in. But yeah, absolutely. And I also post again. We have a LinkedIn group for Just Enough Math. I'll go ahead and just kind of post that. The group will continue as more of a user group under your wise eye, and I'll make you under your tutelage. Thank you, under your tutelage.
Can I make the logo the cartoon?
The cartoon.
I'll tell you this much: once it's in Nick's hands, whatever happens with the logo is up to you. At that point in time, again, if it's in his hands, so yeah. But yeah, and then then just I'll make you like a poster admin, whatever, on the group, so you could post and do whatever. And yeah, again, if you want to change the logo, I'm not going to stop you. So yeah.
What is that?
Awesome. Again, if you need access to the sheet, if you're on a group, I'm going to post it to the LinkedIn group. If you can't access it, whatever, you can go ahead and get a hold of me. I can send it to you directly. But yeah.
Yeah, I just added, submitted a request to be added to the meeting.
Oh, okay. You know what?
If you don't mind, please.
Sure. Let me go ahead and let me also make sure also that. Yeah, I'm doing this right now. Okay, cool. So let me go ahead and get on LinkedIn and I'll.
Just in the short time that I realized.
First official act.
Huh?
First official act.
Just in the
Shabasti, right?
Shabasti, yes, correct.
the short time that
You are now
in the short time since.
Okay, cool.
sent
I've
it to
approved
Pro,
you,
just
and let me go ahead and post. I'm going to go ahead and post right now.
I'll definitely need your help.
Next time meeting still remains as first Wednesday of the month, right? Or
Excuse me?
The next meeting time still remains as first of the month, first Wednesday?
Yeah, it's the first Wednesday of every month.
Regarding.
Yeah, unless there's a holiday or something going on, but otherwise it'll be the first Wednesday of every month. And then of course it's going to be.
Yeah, keep an eye on the LinkedIn just to
Yeah.
make sure, because you and I learned that I'm leading this group at the same time. So like we both learned this within minutes of
You
each
can do
other.
it 2 times a month, and the second time, the second time will be a bad math movie.
Yeah, math-based
Just-
movies.
If you can find bad math movies, I'll.
But yeah, just keep an eye on the LinkedIn, and I'll make sure that it's updated well in advance if there is a date change.
I was putting the post together right